Dans cette toute dernière vidéo,
In this very last video, we will see a natural phenomenon, which is extremely useful to astrophysicists and cosmologists, the gravitational lensing phenomenon. It's a phenomenon also known as gravitational mirage, by analogy with the optical mirages observed in the desert. As the name suggests, it is about the deviation of light, not due to a changing refraction index in the propagation medium, but due to a strong gravitational field, as the one created by a galaxy, a star, a cluster of galaxies. As it passes near a massive object in the foreground, the light coming from a distant body will be deviated so that the background object will be distorted by the foreground object. And by studying the manner in which the subject is distorted, we can deduce the matter, visible or not, in the foreground object, which is then called a gravitational lens. We have already seen gravitational lenses during this class. For example, in the galaxy cluster here with a redshift of 0.397, with a mass of 10 to 15 solar mass. This is an excellent gravitational lens. By zooming on the external parts of the cluster, we can see that there is a whole series of blue arcs which are the distorted image of distant galaxies by gravitational lens effect in the background of the galaxy cluster, which you see here, and which is shown in greenish colors. So we will see in this class how the gravitational lens effect works and why it's such a precious tool for an astrophysicist. We have seen that the gravitational lens effect is essentially a light deflection effect. We will see how to draw this. So a light ray arrives in the proximity of a mass, here the sun, which I represent arbitrarily. The ray will be deviated. We have, for example, here a velocity vector, which will be the light velocity. The ray will be deviated. And to get that deviation, we will have an acceleration. So acceleration does not mean we will have velocities faster than light, but we will have a deviation of the light ray. We will have a changing velocity. We will have a photon that arrives with the velocity of light. We will have a photon leaving after deflection with the velocity of light. And then we will have a velocity difference vector. So the photon will be accelerated for a while. We will get back later on this for a while. The photon arrives with a certain impact parameter that we will call b relative to the sun, or any mass that deviates light. What we intend to compute is the deflection angle we call alpha here. So this deflection angle, if we do some trigonometry, we see that alpha equals the norm of delta v over the norm of our velocity vector, c. Keeping in mind that alpha is always very small, of the order of a few tenths of an arcsecond or of 1 arcsecond, in the strongest cases. Now delta v, what is it? It's the acceleration of the photon due to the sun, in this case here. So gm divided by b squared during some time delta t. So this is the acceleration during some time. It is indeed a velocity. Now the sometime is just an order of magnitude here. We can say that the photon feels the acceleration, will be under the influence of the gravitational field of the sun during some time, which will be of the order of magnitude b divided by c. Beware, this is simply an order of magnitude. Now if we take all these equations together, we will find that it is proportional to gm divided by c squared b. But what we especially see is that the deflection angle depends only on the lens mass, the impact parameter, and physical constraints. And in particular, alpha does not depend on wavelength. Rather, So, counterintuitively, the deviation of a light ray does not depend upon energy or wavelength. In this case here, the result is that if we put an observer Here, instead of seeing the source where it was without the sun, namely in this direction, we will see the light source. So if we had a light source here, one would see it in the direction of this ray here, hence in this direction here. Here we also have alpha. The deflection angle of light by a massive object was measured for the first time in 1919 during a solar eclipse. Note that these ideas are not new. Actually, Newton had already raised the possibility of light deviation by mass. But it is in fact Einstein who predicted the phenomenon for the first time in unpublished notes in 1912. However, the observation only came later on. The observation, which actually provided evidence for Einstein's general relativity theory, was made in 1919 by Arthur Eddington, an English astrophysicist, during a solar eclipse. Note that the measurement principle is simple. We chose a stellar field. So, if we observe it during the night, we will of course see stars at certain positions relative to the sun. So this is a moment when the sun is not in the field of view. The white points are the positions where the stars would be, if we observed them during the night. Now we put before the stars a certain mass. But since the sun is bright, we will only see the stars during a solar eclipse. So here, during the eclipse, light rays coming from the stars will be deflected by the sun, and what we will see are stars, fleeing the sun radially like this. I'm drawing arrows of different lengths, and the length of each arrow is inversely proportional to the impact parameter b, namely the projected distance on the sky between star and sun. So here's the deviation angle of light, each time in a radial direction. So the new star positions with the sun present in this field of view will be the new positions indicated by red dots. Now, how far does this validate general relativity? If we measure, or rather predict, the alpha angle using Newton's theory, namely the little demonstration we made earlier, we would predict 2gm divided by c squared b. But alpha, Einstein, using the general relativity theory, gives back twice that value. That is 4gm divided by c squared b, where m is the sun's mass and b is the sun's radius. And if we took a star which would lie just at the edge of the sun, assuming that we can perfectly measure a star at the edge of the sun, otherwise we would need to rescale by a factor b that we have here. So now the numerical values we have are that alpha is 1.75 arcseconds in solar mass units. Therefore, if we put solar masses here, b divided by solar radius minus 1. That, provided we express b in solar radius units. The measurement taken by Eddington gave 1.75 arcseconds, which is actually the numerical value predicted by general relativity. So the fundamental differences between alpha Newton and alpha Einstein is that using Newton's theory of gravity, we have photons following curved trajectories in an Euclidean space. In the framework of the general relativity theory, we find that photons travel along straight trajectories in a curved space. In other words, trajectories that minimize the travel time of photons. So what we call geodetics, and these trajectories are those of shortest travel length in a curved space. So we have two radically different interpretations of gravitation. And this is what is crucial and has given all the legitimacy to the general relativity theory. Since we construe gravitational fields as acceleration fields and not anymore as forces that masses feel. So here we have a beautiful confirmation of the general relativity theory, simply because the angle measured by Eddington is exactly equal to the angle predicted by the general relativity theory. So now let's see how all this works in more details. We have three important planes. If we draw the situation simply, we have a source represented in orange, which is affected by the lens effect here on the lens plane. This lens can be anything: a star, the sun or another star, a galaxy, a cluster of galaxies, or even, as we shall see, the great structures of the universe. So this source can be imaged. So light will be deviated by an angle alpha that we computed earlier, and the source will be displaced and distorted by the gravitational lens effect. Now the source is located on the sky by an angle beta, relative to an arbitrary position. We will take here a reference point. The position of the images on the sky, as seen from Earth, is located by an angle theta. And then we also have an angle alpha, which of course depends upon theta. We also have different distances here. We have the distance from observer to source, the distance from lens to source, and the distance of the lens. And these distances are angular diameter distances. Now we have a very simple relation between those three angles. That is the lens equation. We have beta equals theta minus alpha theta. That is what we call the reduced deflection angle. Beware, it's alpha, not alpha. It is of course related to alpha. We will see that later. Now we can also express things as a function of linear distances in the different planes. We will put eta here and zeta there, which will depend upon theta. Because if theta changes, zeta changes accordingly. We can even rewrite the lens equation. So here we have angles. They're linear distances. And playing a bit of trigonometry, we will find this. ETA equals delta 1 divided by delta 1s alpha. So there, the alpha appears. Thus, the relation between alpha, theta, and alpha, again by doing some trigonometry in the similar triangles here, we get alpha theta equals delta divided by delta s times alpha eta. So there are some different forms of the very simple equation that is called the lens equation, and which relates to different angles, or angular positions. Let's consider the angular positions of the various objects on the plane of the sky. Beta for the source, theta for the images, and alpha for the reduced deviation angle. We can also relate the linear distances to the different planes, but for that we have to know the angular diameter distances between the different objects. An extremely important characteristic quantity is Einstein's radius. If the source, lens, and observer are aligned, then we have beta equals 0, where the beta angle represents the position of the source on the sky. So, if everything is aligned, we have beta equals 0, which means that the lens equation is greatly simplified. So we have theta equals alpha theta. It's a simplified version of the lens equation. So now, alpha theta, we have seen that it was delta 1s divided by delta s times alpha eta. With eta, if we look at the earlier figure again, and if we do some trigonometry, we have that eta is linked to theta through the distance to the lens, from Earth to the lens. What does it mean exactly? It implies that theta equals delta 1s divided by delta s times gm divided by c squared eta. That is alpha theta, which is linked to alpha. So all that will be equal to delta 1s divided by delta s times gm divided by c squared theta, delta 1. Here, we have a theta here, a theta there. This theta on the other side, I will have a theta e, which will be Einstein's radius, equal to v gm divided by c squared. m is the lens mass. And we will have a distance ratio, delta S divided by delta 1. So theta E is Einstein's radius. That means that if we have a source aligned with the observer, and then we have a lens, a small spiral galaxy, for example, then the light will be able to go through the lens. Since we have a totally symmetric situation, we have a cylindrical symmetry. And this angle here is the Einstein's radius theta E. That means that the image of the source, seen from the Earth, when we have a situation where beta equals 0, so where all objects are aligned, the lens equation has an infinity of solutions which are distributed over a circle with a diameter 2 theta E. And so the source has an image taking the shape of an annulus around the lens galaxy. As an example, here is a real object which is precisely in that case. The mass indicated here, m, is the mass within Einstein's radius. So we see immediately that in this particular configuration, one can measure the mass of a lens galaxy included in the Einstein radius, which is materialized by a circle. The latter is the shape taken by an object, affected by the lens effect in the case of perfect alignment between source, lens, and observer. It turns out that theta E is also a characteristic quantity that gives an idea of the separation between the images of a source in a gravitational mirage, even if beta is not exactly 0. Now, let's consider again the lens equation and look at a simple case where we can solve it. So we have beta equals theta minus alpha theta. We see that alpha theta, if we look at the previous slide, can also be expressed like this as a function of theta E. I said that theta E is a characteristic quantity of lenses. One can simply rewrite the lens equation in a different way, so that here one will have beta equals theta minus theta E square divided by theta. Here, we are solving it in one dimension. One could, of course, have two-dimensional angles. For example, in x and y, if we want to thoroughly represent everything. Anyhow, for a point-mass lens, we have a cylindrical symmetry, even spherical, so the choice of coordinates does not matter much. Now, this is equivalent to a second-degree equation in theta. If we solve this equation here, we will get a discriminant which reads beta square minus 4 theta square times theta E square. So beta square plus 4 theta E square. This is a positive quantity. So we have two solutions, and the solutions, we will call them plus and minus, and they will be equal to 1 divided by 2 beta plus or minus V beta square plus 4 theta E square. So now, we can also divide everything by theta E to have everything in theta E units, since we said that it was a characteristic quantity of lenses. So now we have the angles as a function of the Einstein radius. There, one has 1 divided by 2 beta plus or minus V beta square plus 4 theta E. We are not forced to do that, but it is common practice. So now this, I can call it D. We will write D plus or minus for the signs here. That is a displacement vector which will be slightly bigger than this one here. What does that mean? It means that if I have a lens somewhere in the sky, and I have Einstein's radius, which is like that. Here I show Einstein's radius. That does not mean that the source takes the shape of a circle, but it is the characteristic quantity associated with a lens of mass m. If I place my source somewhere, beta divided by theta E, if we measure everything in arbitrary Einstein units, so if I take an arbitrary beta, it will be beta divided by theta E, which can be found again here. If I add d plus to this quantity here, I will have a mirror image that will form here. This is d plus. That will be the other theta plus image. Theta plus divided by theta, e, since we measure everything as a function of the Einstein radius, and then, so my source is here, I will write a quantity d minus, equal to the norm in the other direction, so on the other side. So I will get somewhere around here. I have d minus. This will be the second mirage image of the source that I will call theta minus. So we see here that in the case of lenses, we have a point lens, which means that the whole mass is concentrated in one point. M is a constant as a function of the radius theta. If the lens is a point mass, we'll have two mirage images on either side of the source. So these are the two mirage images of the source, which were here originally. And this is where was the object, that is the lens. As we have just seen, photons can be deflected by gravitational fields. So on this figure we see a gravitational lens effect on a distant quasar, the very bright nucleus of a distant galaxy, hosting a supermassive black hole. When light rays from a quasar pass near the lens galaxy, the foreground galaxy, they are deflected, and the image of the background object, the quasar, is modified. We have seen in the previous slides that in this simple case of a point mass lens, we predicted two mirage images of the background object, the quasar, in this instance. But actually, when the models are a bit more realistic, we predict that we always get an odd number of images, 3 or 5, depending on the shape of the foreground lens. In the animation shown here, one sees in fact 4 images of the quasar, the 5th image lying between the 4 images, distributed around the lens galaxy. And the lens galaxy, because of its brightness, masks the 5th image. So we talked earlier about Einstein's rings. We have just seen in the video in the previous animation 4 mirage images of a quasar. Now what happens if instead of a point-like source, the latter is slightly extended? And if the source is perfectly aligned with the lens, we obtain, in that case, of a situation like this, a perfect Einstein ring. Here is a lens galaxy with a redshift Z1 of 0.45. We have a source, the redshift of which, Zs, is equal to 2.38, in this case. And we see at once, here, the Einstein ring materialize. I'm drawing it here in red, but it is already very well defined by the blue background galaxy at Z equals 2.38, which appears as a very distinct Einstein ring. What we see here is the Einstein ring. Now we have said that theta E equals V gm divided by c squared, delta 1s divided by delta s times delta 1. And we have a distance ratio here. So we have distances, and we need to convert the red shifts into distances using a cosmological model. So if we have that equation here, then we inverse the equation, and we deduce from it the mass inside the Einstein ring. Now, it's the mass inside theta E, but the viral would also give us the mass within a certain radius r that can be chosen arbitrarily. So, if we measure the velocity dispersion of the stars within a certain radius r, we have seen in this chapter about dark matter that mass is related to the dispersion of the radial velocities in this way here. This means that if we measured sigma r through the Doppler effect in an aperture as shown here, here we have a certain radius, a certain sigma r measured by Doppler effect. We'll have the mass within a certain radius, and the mass inside the Einstein ring, which is here. So we'll get 2 mass estimates inside different radii, meaning we'll have access to the mass gradient. It's extremely important to constrain the models of galaxy formation that are produced through numerical simulation. The mass gradient measurement is possible partly through this gravitational lens effect combined with the velocity dispersion in well-chosen apertures. We already see that the strong gravitational lens effect, strong because it produces large mirage images of background objects. We see that the gravitational lens effect is an extremely powerful tool to measure mass as a function of radius, and we can measure the luminous mass and the total mass thanks to this phenomenon of gravitational lensing. Since it only depends on gravitation, we do not need to see the mass to measure the effect it has on background objects. Last example, there are in fact multiple applications of the gravitational lens effect. We will not describe them all here. We have seen the strong gravitational lens effect, which produce multiple images of background objects, namely Einstein rings. Now we'll see the weak gravitational lens effect. It's an effect which causes weak deformations of background objects, but it is also present everywhere in the universe. Here we see a slice of the universe. It's a numerical simulation. We see different slices of the universe at different red shifts. We see evolving structures. We have a red shift of 0. This is the present epoch. Here we have a red shift. It's a numerical simulation. In the numerical simulation, the redshift was of 1.4, and here we have a redshift of 5.7. Now, if we take some light rays coming from far away, the light rays will intercept each plane. We'll have a deviation of light, which arrives, for the example here, in this plane here. It will be deflected again by a mass lying. For example, here. It will arrive at the plane around the present epoch. If we have the image of a background object here, for instance, we'll see its distorted image by lens effect, and we'll see it distorted at its arrival, hence at the present time, where we observe the background source. So this effect is very weak. We need to measure it on a lot of galaxies and take an average to see it, but it is something detectable. Of course, the effect will change as a function of what we put in the different slices of the universe. The deformations predicted by the cosmological models will change as a function of HO, of the composition of the universe, of the composition in terms of dark energy and dark matter. We will not have the same predicted universe, and so will not predict the same deformation. The point here, the goal, will be to measure the distortions of these extremely distant galaxies using this mirage effect, which is weak. We, of course, exaggerated the light deviations to be able to constrain the cosmological models. In practice, how will we proceed? We take a slice of the present universe. This is a simulation. In practice, we do not see the simulated filaments. Actually, the galaxy clusters. Here, we have gigantic scales. The galaxy clusters can be found at the connections between the filaments, but filaments are essentially composed of weakly luminous matter and dark matter. Now, assuming that the background galaxies are round like this, I'm placing them like this. There are, of course, billions. I only have a few. Some of them are near each other. Others are far away from each other. Each time the rays are deflected, what will happen is that a circular galaxy will be distorted into a small ellipse by the lens effect. The distortion will be tangential with respect to the direction of the mass. A round galaxy and some mass here, they will be distorted by lensing effect. I'm exaggerating the deformation a lot, but in this manner, here, if we have a massive filament going through here, the distortion will be like this. Here the distortion will be like this. We can draw a lot of others. I cannot show them all. But here, for example, we have several galaxies distorted by approximately the same filaments. Here, there is another like this. We can see that the shape of galaxies, which are affected by the same filament, will obviously be more correlated than galaxies distorted by filaments laying very far away, angularly on the sky. So here, between two galaxies, we have an angle theta, there another angle theta. What we'll be able to measure in practice is what we call the 2 points correlation function of the shapes of the galaxies. This correlation function, we'll omit the details here. We'll call it ETA, theta. We have here the theta angle. The typical scales are 10 arc minutes to 100 arc minutes on the sky. Hence the importance of taking wide field images. We want to measure the correlation function over very large scales. So for small angles, we'll look at the correlation of the shape of galaxies which are separated by a certain angle theta. Then, of course, the galaxies that lie close to each other feel a lens effect due to the same filaments, so the correlation is very strong. Galaxies laying far away from each other, hence at high theta, will be much less correlated. What we expect to see is a correlation function that will decrease like this. The goal is to measure the distortions of all galaxies over the whole sky, and to measure the shape of all galaxies over the whole sky, and to measure the correlations at every scale. The idea is to take the most precise measurement points here, to discriminate between the different curves, the different correlation functions, here, which are predicted by the cosmological models. The cosmological models will predict the correlation function, or a power spectrum, which will be a function of theta, of course, of HO, and then of cosmology. Cosmology is, among other things, HO, but also the densities of the different components of the universe, namely dark matter, dark energy. Thanks to these measurements of the weak gravitational lensing and of the correlation function of galaxy shapes, everywhere in the universe, we can constrain cosmological models, provided we have, as far as possible, a map of the whole sky with a very high spatial resolution. The gravitational lens effect manifests itself at all mass scales and at all spatial scales, from stellar scales, or even planetary ones, to galaxies or even galaxy clusters. We have seen that the largest structures in the universe, the cosmic filaments, produce a weak but measurable lensing effect, and that these measurements allow us to determine the cosmological parameters, the parameters which describe how the universe is evolving, and what its composition is. The data for this ambitious goal will be produced by the Euclid satellite of ESA, which, starting from 2020, will measure, with exceptional quality, the shapes of billions of galaxies to see, statistically, how the images are distorted by the whole of the cosmic structures, over a field of view which corresponds to a third of the whole sky. So for now, the future of cosmology depends on our ability to map the whole universe and not just some well-targeted areas, as we were able to make until now. This concludes this week of lectures. In our MOOC of Introduction to Astrophysics, we have introduced a large variety of topics and described physical concepts hiding behind astronomical observations and their interpretations. The goal has been to understand the principles rather than the detailed mathematical developments. I hope this goal has been achieved. But I especially hope that you took as much pleasure in following this course as we had preparing it.